We're going to finish up chapter 5 today. We'll have a test on Friday, chapter 5. To review, really pretty much the whole chapter, we're just going to go all the way back and review the whole thing before we get started, because we don't have just a whole lot to cover today, and some of what we cover, what we will cover is just kind of a continuation of what we talked about on Wednesday, and generator types and things like that. So what we talked about are different types of imaging systems and how we categorize imaging systems, and we categorize them by energy and usage, and we talked about the differences between those, between therapy and diagnostic and mammography, fluoroscopy and diagnostic, RF rooms and all that. So we talked about the characteristics of a table in a room that is an RF room or a just a diagnostic room, and that is that it had to be, it's usually made of carbon fiber, but it could be any kind of radiolucent material, but it has to be radiolucent and of uniform thickness. We talked about in fluoroscopy tables, we've got to be able to move the bucky up and down the table so that we can get it out of the way of the fluoro tower, but we also talked about it in context of movement and the difference between diagnostic tables and fluoroscopic tables. Diagnostic tables are going to be unlocked with locks and they're freely floating, as opposed to fluoro tables are motor driven, right? We talked, one thing we didn't talk about is the degree of tilt of a table, and you see that on page 86, and they'll categorize the degree of tilt on a fluoro table by how far it will go in degrees in one direction versus the other. And it's kind of stuffy in here, isn't it?
Yes.
Yeah. Let's see if we can adjust that. So if it goes, standing up, well, a tabletop that is parallel to the floor would be at 0 degrees from the floor, right? It's parallel to the floor. So if it's perpendicular to the floor, then you've got a relationship where you've got 90 degrees, right? So if it stands straight up, which all fluoro tables should stand straight up, then that would be 90 in one direction. 90 in one direction. So your fluoro tables will be identified by how far they'll go in both directions. So if you've got one that's 90-90, that means you can stand a patient on their feet, stand a patient on their head, right? Most of the time they don't go that far in one direction, and they go 90-50 or something like that, which means that you can stand them on their feet, but you're only going to go a certain degree in the opposite direction. So you identify those by degree of tilt. And all your fluoro tables, unless you're working on a cysto table or something like it in surgery, your image receptor was on top. So with the image receptor on top being the image intensifier, underneath is where your x-ray tube was. And that left with that bucky a big slot, big open space that you had to cover up, and we covered that up with a bucky slot cover for radiation protection for you. So we talked about the operating console and what all we control at the operating console is quality and the quantity of the x-ray beam. We control a lot of stuff there. We can control KVP, MA, time. We can control what kind of timers we use, whether they be a phototimer or usually an electronic timer. More on timers again in a minute. But we could select focal spot size. We could select a lot of different things, right? Which bucky we were shooting into and all that. So that was one portion of the imaging system. Another portion of the imaging system was your high voltage generator system, and then the other portion, of course, is the x-ray tube, and we'll talk about that in a future chapter. So then we talked about selection of KVP. Selection of KVP occurs at the, wow, at where? What are you doing whenever you select your KVP? The auto transformer, very good. It's at the auto transformer. So what you're doing is you're selecting contacts on the, you're selecting contacts on the secondary side. Contacts on the primary side are for the most part set. So you're selecting contacts on the secondary side. So if you mash them together, then your voltage goes up or down. If you you mash them together, it goes down. If you pull them apart, so if you have them wide apart, then voltage goes up. Do you have kilovoltage at this point? No. This is a voltage manipulation for safety, for your sake. We use relatively low voltage. If we have kilovoltage at this point, it'd be much more dangerous. So coming out of the secondary side of that, this is our KVP selector, but we don't have KVP yet. We said that we're going to put as much as we can to get in the low voltage section for safety. All right, so it comes out of that and it goes into a transformer. And there are more turns on the primary side or secondary side of this transformer? What's that? Secondary side, right. So we got secondary side. We've got more turns on the secondary side. That makes this a step up transformer. So we've got primary side, we've got secondary side. This is a step up transformer. And what is the purpose for this particular transformer? Good. Take our voltage that we have set here, and we're going to make kilovoltage out of it. Right, at the same time, we've got a secondary circuit that comes off, and it goes through, well, we'll call this thing and this thing a rheostat, exactly. In this case, it was an auto transformer, variable resistor. This is also a variable resistor, but it's an MA selector, and they are both rheostats, right? So this is our MA selector. It goes into another transformer that has more turns on the primary side than on the secondary side, so it is a step down transformer, and then that comes out and it goes into the where? Filament. Very good. So what's the purpose for this this circuit down here? To what happens when we send electrons through a circuit? What do we create? Two things. Thermionic emissions, exactly. We're going to get thermionic emissions. Somebody may say, well, you get a magnetic field, which is true, but that's not what we're interested in here. We do get a magnetic field because we send electrons through the circuit. But what we're interested in doing is heating up the filament. That's the only thing that we're really interested in. Past that point right there in creating is heating of the filament. So we get thermionic emissions, right? When do we get thermionic emissions? When does that occur? Whenever you press the prep button, right? Now, here's one thing that we didn't really talk about, and that is that you've always got a filament current running. It's not until you press the prep button that this thing heats up to the point of thermionic emissions. The reason we've always got a filament current running through the filament circuit is because the main thing that kills an X-ray tube is heat, right? And it comes from a lot of different directions. We create a lot of heat. We send that heat across the X-ray tube and we bombard the target with heat. But at the same time, compared to the classroom today, what are your X-ray rooms usually filled at? The hospital in general? Cold, right. So what we do is we run a low amperage, low voltage and low amperage through that filament just to keep the X-ray tube a little bit warm. It's not hot enough to do any kind of damage, but it keeps it a little bit warm because if we put a big exposure on that filament, or we put a lot of thermionic emissions on that filament, and the filament's cold, it's kind of like throwing hot water on your windshield in the wintertime to get the frost off the windshield. What's going to happen? You're going to crack it, right? And even if that doesn't crack, if you take all those electrons, you send them across the tube when you make your exposure and they hit that big plate and that big plate is cold, then what's going to happen to the plate? It's going to crack it, right? So there's always a filament current running. So we didn't touch on that, but just be aware there's always a filament current running through that. All right, so what kind of current do we have to have here? Alternating current, so that we can create a changing magnetic field, so that we can induce a alternating current in the secondary side. So what kind of current do we have to have here? Alternating current for all the same reasons. What kind of current do we have to have here? Alternating current. What kind of current do we have to have here? Direct, right. So it comes out of this, and what does it go into? What does it go into after it comes out of the high voltage transformer? problem, we have direct, or alternating current, we want direct current. How do we fix the problem? We rectify the problem with rectifiers in this case, right? So how many rectifiers we're gonna have? Four. We're gonna have 4 rectifiers, and what that does is it takes the electrons that are, normally go in that direction, but whenever they try to come back in the opposite direction, they try to come back in that direction, what they're gonna do is they're gonna feed back down. We're gonna have 2 pulses in the same direction. All right, so what do we have at that point? Direct current. It's pulsating direct current. Even if we didn't do this, would we have direct current? Yeah, because it's only going in one direction, but by adding it, we double the output of the X-ray tube and make X-ray creation a little more efficient. Now, we also talked about incoming line voltage, and that power fluctuations in the hospital are just like power fluctuations in your house. The air conditioner kicks on, the lights tend to dim, right? So we talked about a different circuit that really comes before the auto transformer. What do we call that? Line voltage compensation, right? So line voltage compensation, how did you manipulate line voltage compensation? It's a trick question. You don't. It's just a circuit that's built into the machines. If you happen to see or work with a single phase machine, you'll see a control for that on the control panel, but chances are you're not, unless you go work for a vet's office or a small doctor's office in the middle of nowhere, you're just never gonna see that. But just be aware it's there. Okay, so it's basically a surge protector, and it makes your KVP set before it gets to here. If we can manipulate it here and get the voltage we want, then because we got a set turns ratio here, we know exactly how much voltage we're gonna have on the secondary side. All right, so we talked about all that, and then we talked about the different types of timers. We talked about synchronous timers. And synchronous timers, where did we see synchronous timers? So you're probably never going to see equipment that utilizes synchronous timers, but there's a telltale indicator that you're working with machines that use synchronous timers. What was that indicator? Been a long time since Wednesday, right? So they work off of the voltage waveform, right? So voltage waveform, because what we did was we changed alternating current to direct current, we are using the negative side of the voltage waveform. So the voltage waveform that we're actually utilizing looks like that. We said alternating current changes directions how many times in a second in the US? 60 times a second, right? So it changes direction 60 times a second. But if we take that negative side and we flip it up, how many pulses do we have? 120 pulses. And so for a synchronous timer works off the incoming line voltage. So since we have 120 possible pulses, our synchronous timers are going to be set in increments of 1/120th of a second, right? So the shortest exposure time you can get is at 1/120th of a second for synchronous. And then 1/60th, and 1/40th, and 1/30th, and so on, right? So about the only time that you're going to see a synchronous timer and how you're going to know you're working with single phase equipment, because this only works with single phase equipment, and that single phase equipment has a synchronous timer, is that you're going to be looking at fractions instead of decimals. Your timer setting is not going to read out in milliseconds, they're going to read out fractions, 1/120th of a second. Okay? So very accurate, but very limited. So we talked about manual timers, you just don't see those anymore. We talked about electronic timers, and electronic timers were what you work with now. Electronic timers allow for the shortest exposure time, and they're the most accurate. I don't really, logically, I can't make the leap of understanding how this could be any less accurate than a electronic timer, but whatever, we'll go with the literature. picture and say electronic timers are the most accurate. So shortest exposure time, most accurate, and that's what you're going to be using. We talked about what a mass timer was, and where did we say you see a mass timer? Portables. It's on a machine that is limited and it typically only has a single MA station. And so what you're actually doing when you adjust your mass is you're adjusting your time. So mass timers are really just timers that you adjust the mass by adjusting your timer. Then we talked about the different types of automatic exposure controls. We've got photodiodes. Photodiodes are behind the image receptor, and ionization chambers in front of the image receptor. So the characteristic of the ionization chamber is it has to be radiolucent, right? So it has to be radiolucent, but regardless of which type you use, it's just a counter for radiation. So if we have a hypersthenic patient, we have the same KVP set. What's going to happen in order to get the accurate exposure to the image receptor? More time, right? So if you have a thinner patient, then you're going to have less time. So you're adjusting the KVP. What would that do? We didn't really walk through that, but what would that actually do? Change the amount of time. That's all it's going to do, because it's still going to require that same exposure to the image receptor. So how many of y'all, and I know what the answer to this is, every one of you should raise your hands to this. How many of y'all have set a technique in your phototiming and the tech comes in and adjusts the KVP just a little? Every single one. You're going to do the same thing because you're going to get it in your mind that you've got to touch it. But realistically, if you're phototiming and you adjust the KVP, it's not going to have any effect on the exposure to the image receptor. It might have an effect to the exposure to the patient, but to the image receptor, it's not going to have any kind of effect at all. You increase your KVP, it shortens exposure time. You decrease your KVP, and it increases exposure time. So that was that. So we talked about voltage rectification, high voltage generator. We did in the last section. Voltage rectification was a process of changing alternating current to direct current. We still have pulsating direct current. We're never really going to have non-pulsating direct current unless possibly we're dealing with a machine that works directly off of the battery and doesn't run through all this stuff. I can't imagine where you would see that. So it's also always going to be pulsating direct current. It's just that the pulses get smaller and smaller, and that's what brings us up to today. Any questions on, well, we did talk about the rectifiers themselves, where we have a solid state diode. We've got two silicone pieces joined together, one with N-type, one with P-type. Characteristics of the N-type were that they were negative, which means that they have an excess of electrons, right? The characteristic of the N-type was that it was positive. It had electron holes, which means it has an absence of electrons. Same answer, right? So that if you apply a current to the inside, then what do you get?
No flow.
To the inside, you get flow. If you get you apply electrons to the P side, then the holes go towards the wire and it vacates the P-N junction. You got nothing. All right. So in that way, you can change alternating current to direct current. All right. So any questions on all that before we go into generator type? So we've essentially got 3 generator types, and one is, well, 2 of them kind of have subtypes, so to speak. All right. So if we take and we get our voltage waveform, we've got unrectified voltage, like that. So what theoretically could happen is we'll have alternating current going through our tube, and we talked about this on Wednesday. Alternating current, when the current's going in that direction, we're good. But whenever the current tries to come back in this direction, if it actually does, then we can break our filament and It kills the tube right away. So the only time that you're gonna have unrectified current would be either a total failure of your rectifier bank, or you're working with a dental unit. Dental units don't use enough kVp to get that reverse voltage. So they use the x-ray tube actually becomes the rectifier bank. So what they've really got is, oh, okay. What they've really, it was weird. I went like that and it tried to pull it out of my hand. I was like, what? You know, do we have a ghost in here? Halloween's over. So the x-ray tube actually does this. That's what you call a self-rectified unit. Again, unless you're working in a dental office, you're never going to see those. Even our Panorex units don't use that. Our Panorex units take and run the alternating current through a rectifier bank so that what we have is that plus the negative side flipped up, okay? Understand rectification is just the process of taking AC to DC. That's all it is. So that is rectified, right? Because it's direct current, it's only going in one direction. But what we get is not only rectification, but inversion of the negative side of the voltage waveform. So we get double pulses. This is what we call half-wave rectification, because you're only using half of the wave. Does that make sense? You're only using half the wave, so therefore it's half-wave rectification. This is, in comparison, full-wave rectification, because you're using the entire wave. Right? So that's, again, what you're going to be using if you ever work with a single-phase machine. That's what you're going to be using is full-wave rectification. So the power company can supply what we call three-phase. And with three-phase generator, three-phase power supply, what we get is not just a single set of pulses like this. You know, we still have to have alternating current all the way through this. So we've got three different pulses running through all this all at one time. But once it gets to rectification, let's take it all the way back to half wave. So if we've got three pulses that overlap, but they stagger, then what we're going to have is a pulse that starts, and then whenever it reaches its peak and it starts to come back down, we send in another pulse, and this is so much harder to draw than what you might think it would be. So we've got two pulses that overlap, and then whenever that one starts on its down cycle, we send another pulse in, and they look like that, okay? So now, if this represents, what this represents here is the magnitude of the voltage. Okay, so at this point right there, we've got 0 volts. At the peak up here, we have the highest voltage that we have set. So if we have set 100 volts or 100 kilovolts, our voltage, you know, what we set on our auto transformer was 100 kVp and our machine shooting accurately, then that's going to be at 100 kVp. Okay, that's going to be at 0. So what we do in doing that is our overall beam energy never drops to 0. Each pulse does drop to 0, but the overall beam energy doesn't drop to 0. I'll talk a little bit more about that, and it kind of gets us a little bit deeper into the semester here. I'll talk about that here in a minute. But the waveform becomes much more constant, right? It doesn't go all the way down and stop making x-rays. It becomes much more constant. We're still unrectified at this point, but if we run it through a rectifier bank that utilizes at least 4 rectifiers, then not only can we change this from alternating current to direct current, but we can also flip up those negative pulses and overlap them like that, okay? So I had 3-phase, I had single phase, so I had 1 pulse per cycle, right? And then I rectified it and inverted the negative half. How many pulses did I have now? Do I have now? 2. Then I sent 3-phase power in and I unrectified it. How many pulses would I have? 3. And then once I rectified it and inverted the negative side, how many pulses do I have? 6, right. So this is a 3-phase, lollipop looking thing, stands for phase, 6-pulse rectifier, or generator system. All right? So 3-phase, 6-pulse. And that was a step towards a more modern machine type. It took place probably late 70s, early 80s. Okay? Improved the output, increased the output of the X-ray machine by increasing the pulses. It also gave us a higher average voltage. Our voltage never dropped to 0, so it gave us a higher average voltage. Now, what we're going to learn later in the semester is that KVP is not the definitive authority, so to speak, on beam quality. There's a lot more that goes into beam quality than just KVP. We call KVP the control beam quality because it controls peak energy and how likely that X-ray beam is to penetrate through the patient. But anything that increases the average and prevents our low energy photons from either being emitted from the X-ray tube or striking the patient also increases quality. Okay? So the key in that whole thing there was prevents from hitting the patient. Okay, low energy photons prevents them from hitting the patient. What do we talk about in like the second week that that the dentist instituted to prevent those low energy photons from hitting the patient? It's been a long semester. He did 2 things. One was beam limitation collimation. What was the other one? Filtration. Bingo, filtration. So this is output at the anode. Okay, so it never drops completely to 0. Each pulse does drop to 0, but the overall beam energy never drops to 0. By the time we introduce filtration, then what we're going to do is we're going to eliminate all that. So what we're left with conversion from single phase, 3-phase is an X-ray beam that once it emits from the X-ray tube truly does not ever drop to 0. So we get a much higher beam quality. Does that make sense? Because the average goes up, we never drop to 0, so these low energy photons are gone. They wouldn't do anything except for absorb inside of the patient anyway, so they're useless for us. We need photons to penetrate through the patient. So it never drops to 0, the average beam energy increases, and therefore the quality of the X-ray beam increases. You good with that? Okay, so somebody came along and they said, well, that's great and all, but what we've got there, you know, when we had single phase, regardless of if it looked like, you know, that or that, our voltage, our power dropped to 0. Not only did it drop to 0, but the distance between the peak and the minimum energy, the swing there was 100% in both of those. And they called that voltage ripple. All right, so 3-phase 6-pulse, that voltage ripple is about 14%. All right, so what if we could increase the average even more? What if we could take and we could kind of smooth out those pulses, or not really smooth out those pulses, but what if we could increase the number of pulses in between each one of these and reduce it even more? So if we sent basically 3-phase 6-pulse into a system that would bounce the voltage off of itself so that it's going in one direction and it knocks it back, and we get 2 pulses that are out of phase with each other. So we got 3-phase that's now out of phase with itself, 2 pulses of 3-phase that are out of phase with itself, so that we get 3-phase 12-pulse. Do we not again increase our average energy? Do we not increase the efficiency and the output of our X-ray beam, X-ray tube beyond this, and have less voltage ripple, less of a change in swing between peak and the minimum energy? The answer is yes. So with 3-phase 12-pulse with 6 pulse, we get 14% voltage ripple. With a 3-phase 12 pulse, it's around 3%, so it's pretty consistent. And it's still not enough for somebody. You know, that was enough for me, but it wasn't enough for somebody. So somebody came out with what they call a high voltage or a high frequency generator. A high frequency generator does all that stuff, but it runs it through another circuit that, as I understand it, how it works is like this. Right, so what you get when you make the exposure, you're at 0 voltage because you're on prep. You make your exposure, you send the electrons across the tube, and what you get is let's say you set 100 kVp. What's your voltage ripple on 3-phase 12 pulse? 3%. 3%, right. So you set 100 kVp. What the machine sets for you is something closer to 103 kVp. Okay? So it sets, even though you set 100 kVp over here, your machine is set to give you a greater output or a greater kVp. So you make your exposure and it boosts it to a point where now you're on 3-phase 12 pulse, so you've got this 3% voltage ripple, and that 3% is fluctuation at top and bottom, and what it does is it comes back in, the voltage waveform is cut off at 100%, so that your voltage ripple just all but disappears. So you've got really, really close to a constant potential. So your kVp is almost constant throughout your exposure. Is there a little bit of a ripple? Yeah, there is. But it's less than 1% on a high frequency system. Okay? Every new machine that you see that you'll get probably within your career, again, unless you're working at a small clinic somewhere in the middle of nowhere, you're most likely going to be looking at a high frequency system. Okay? So the high frequency system, you can tell audibly, you can tell when you're working with a high frequency system. When you make your exposure, you should hear a beep coming out of your console, but somewhere in the room, and if it's up in the ceiling, it may be hard to hear, but listen really, really carefully. In a lot of cases, you'll hear a squealing sound whenever you make your exposure. You ever heard that? You make your exposure and you not only get the beep here, but in the room you hear eep, something like that. And that's that circuit that does that. And what they call that is a chopper circuit. Chopper circuit chops the peaks off, basically, all right, so that you get a constant potential, or very close to a constant potential. Okay? So you look at all this, and you go from single phase to 3-phase 12 pulse, we'll say 6 pulse, to 3-phase 12 pulse to high frequency, then you're looking at an output, increase in output in each one of those. And it sounds like it's pretty significant, right? You go from single phase to 3-phase, and it sounds like your conversion there, or the amount of output that you would see, the change in output that you would see between single phase and 3-phase would be how much? It seems like it'd be 3 times, right? It's not. That'd be too easy. So you would think that from single phase to 3-phase 12 pulse, it would be, well, from 3-phase 6 pulse to 12 pulse, it would be a factor, again, of 2, right? And then from 3-phase 12 pulse to high frequency, it'd be something else. It's really not that significant. From single phase to either one of these, you're looking at a factor of 2. And from single phase to high frequency, it's about 2.5, okay? So you're gonna have questions that say something to the effect of, bless you.
Thank you.
If you make a good exposure in a single phase room, you got a good exposure in a single phase room, and for whatever reason you got to repeat the exposure to take a patient to a 3-phase room, then what are you going to have to do? You got the right idea, you're going in the wrong direction. You're going to struggle with this, I'm going to tell you now, all the way through your second year, okay? Even though you're never probably ever going to see this, you still got to know it, and you're going to struggle with it all the way through the second year. If you go from three-phase to, single-phase to three-phase, then your output increases, which means you need to decrease your technique by a factor of 2. So let's say you shot a chest x-ray, KVP is irrelevant at this point because most of the time our technique compensation is going to follow mass, okay? So you shot a chest x-ray in a single-phase room and it had 10 mass, then what are you going to need in a three-phase room? 5, right. So in a three-phase room, you're going to need 5. In a high-frequency room, you're going to need 10 divided by 2.5 is going to be roughly 4. Okay? So if you go in the opposite direction, you take the perfect x-ray in a three-phase room, and now you've got to switch out to a single-phase room, and you're now you're shooting KUB, and in a three-phase room, you use 32 mass on a KUB, which, what are you going to need in a single-phase room? 64, exactly. You're going to have to double it in order to get the same exposure. Okay? So your technique compensation is mass. That's number one. It's mass, and your the actual magnitude of your compensation is 2 times, or it's a factor of 2, for change from a single phase, three phase to a single phase. If you change from a single phase to three phase, your technique goes down. That is because you got an increase in output. If you don't do anything, all right, let's walk back through this again. I know I kind of just jumped off tracks there. But if you don't do anything, you shoot a perfect x-ray in the single phase room, and you use the same mass in the three-phase room, what's going to happen?
Burn through it.
Huh?
You'll burn through it.
Yeah, you're going to overexpose the patient. Your mass is going to be twice too high, right? So if you go from three-phase room to a single-phase room, then what are you going to have?
Times it.
Yeah, but if you don't adjust your technique, then what are you going to have? Underexposure, right? Okay. So if you're going from a three-phase room to a single-phase room, you use 32 mass on KUB, you have to use 64 in a single-phase room. Okay. So it's double output. You're gonna get to the test and you're gonna have tendencies to think single-phase, three-phase, factor 3. No, it's factor 2. Yeah.
So if you go from a single phase to a high frequency, is it 2.5 then?
2.5.
Okay.
Yeah. And this was 20 years ago, but I actually worked in a hospital, and the ER was a mess. It was a mess. Probably the busiest ER in East Texas. And they had a high-frequency room that was basically a doctor's office room in one room and a single-phase room in the other room. And, it was, and the single-phase room was on phototom too, so, you had to know your techniques and you had to be able to make the adjustments. The hospital itself was a mess. We had a three-phase room that I think had some burnout rectifiers because the techniques didn't work anywhere on the planet like what they did in that particular room, let alone in the x-ray department. But you're probably never going to see that. I haven't seen a single-phase machine in a hospital. That was the only hospital I ever saw a single-phase machine in. All right, so any questions on single-phase, three-phase, high-frequency, single-phase, half-wave? Yep.
What if you go from a three phase to a high frequency though? Do you ever do that?
No, you really don't have to do anything. It would seem like maybe because you're going from 2 to 2.5, but have y'all been through technique correction in trainings class yet? How much of a change in technique you have to see a noticeable difference as far as KVP and mass goes?
Like 15% rule?
Close. The 15% rule is if you wanted to double your density with KVP, you would increase your KVP by 15%. If you wanted to affect a change in grayscale, you would change your KVP by 15% and adjust your mass by a factor of 2. That's your 15% rule. But the rule of thumb for technique adjustment, if your KVP is right and you just need to affect a change in exposure, then you adjust your mass. And generally, if your mass is worth adjusting and it's worth retaking an x-ray on a patient, then your your mass adjustment needs to be a factor of 2. So if you underexpose a patient to the point that you need to reshoot the patient, then you either need to increase your mass by a factor of 2 or decrease the mass by a factor of 2, okay? 30% is the baseline for just the minimalist change to make, okay? So it's never worth repeating an exam for a 30% change, okay? Now I did all that to run through this. So 2.0, you know, that's your factor from single phase to 3 phase to 2.5. What's the difference numerically between that? It's 0.5, right? But how many 0.5s do we have in 2? 0.5, 1, 0.5, 2. Right? So there's 4 of them, right? So if we divide 100 by 4, what do we get? 25, right? So if we have $1 and we have a quarter, then we have 25% of the dollar, right? So the minimum amount that you need to change for a change in mass, because you need to repeat, is 30%, well, to repeat is a factor of 2. But to even see any kind of difference is 30%, right? So that's 25%. It's really not worth running through the mental gymnastics to make the change. Could you? Yeah, but really the techniques will work. And visually, you won't be able to see a difference if you don't make a change. So that kind of makes sense. There's a long way to go to get to that, but I wanted you to understand the reason. Because it looks, just looking at the numbers, like you need to make an adjustment, but you really don't. Because the amount of output difference between 3-phase 6 pulse or even 3-phase 12 pulse in high frequency is only about 25%. And that's just not enough to get in a twist about it. Okay? All right, so we do have any other questions on all this? Yeah.
Just real quick, so if I go from a 1-phase to a 3-phase with 6 pulse, I'm changing it by a factor of 2.
Yeah.
If I go from a 3-phase 6 pulse to a 3-phase 12 pulse, it doesn't matter because it's 25% difference. And then from a 3-phase to a 12 pulse to high frequency is 2.5?
No, the 3-phase 6 pulse to the 3-phase 12 pulse, really effectively, there's not any change. There's a slight increase. So if maybe you knew that you had 3-phase 6 pulse, then maybe you might get to that 30% if you went from 3-phase 6 pulse to a high frequency. So really not any technique adjustment between either 3-phase to high frequency, or certainly not any change between 3-phase 6 pulse and 3-phase 12 pulse. Okay. Anything else? Okay. So we do have a couple of different types of generators as well, and you may or may not see either one of these. First is what we'll call a capacitor discharge unit. Does anybody work with a portable machine that feels like it's really, really light, and in order to use it, I'm not talking about to charge the batteries, but in order to use it and make any kind of exposure, you take it up to the patient's room, and you plug it into the wall before you can shoot with it? No? There are some out there, and some of those use what we call, not all of them, but some of them use what we call capacitor discharge output units. Can I erase this? So a capacitor discharge unit, a capacitor is kind of like a one-shot battery. All right? So what you've got in a capacitor is kind of like 2 electrodes, kind of like in the X-ray tube, but what you've got is a layer of insulation in between them, and it's kind of like, and I'm going back to where we're talking about static electric charges, and you holding on to a static electric charge in the wintertime, you essentially become a capacitor. So a capacitor discharge unit, what it has is it's got electric flow into one side, and then what you've got is kind of a storage tank for electrons. So you got this great big plate, and then you've got another plate on the opposite side of it, and it may not even be as big, and it works kind of like a fuse. And you've got an air cushion in between them so that the electrons cannot make that jump between here and here. So basically what you've got is something similar to your X-ray tube when you're in prep, but you hadn't pushed exposure. So the electrons can store up over here, so you got this collection of electrons. The law of electrostatics says that the more electrons you have, the more charge you have, right? So you can store up all these electrons on this one side, and they're not going to flow across. But whenever you're ready for them to, so you've got all this stored over here, but when you're ready for them to, you can bring these things closer together or do whatever you need to do to break down the insulating factor in between the two, and the electrons will jump across. That's a capacitor. So you build up a charge in a capacitor. When you're ready to use the charge, you discharge it, okay? So some of our X-ray units work off of that principle, some of your older units. And what a capacitor discharge unit does is you make your exposure, let's say you set 100 kVp, then you store all these electrons, you make your prep, you make your exposure, these things draw closer together, the electrons jump across, and what you get is discharge of the electrons. Now what are the laws of electrostatics? Again, the more electrons we have, the more electrons we have, right? The more electricity we have, the more charge we have. But the distance in between them, right? So the electrostatic charge decreases by the square of the distance in between them. So we cram them all together and we get a big charge, right? We got a lot of electrons we cram together, we get a big charge. But once we let them go on the other side, what are they going to do? They're going to spread out. Right? They're going to spread out. So here's the key to a capacitor discharge. Once those electrons jump across, they're still going to be crowded together, so your 100 kVp works as 100 kVp. But throughout the exposure, because they're starting to spread out, your voltage drops to a point where eventually it's just ineffective at some point. So what you have with a capacitor discharge unit is basically a single shot battery. You got to plug the machine in, build up this charge, get the charge ready, make the exposure. Once the exposure is made, your kVp drops consistently throughout the exposure until it just gets to a point where, you know, it's got a useless charge at that point. Okay? That is not to be confused with a falling load generator, which is next in the textbook. Falling load generators kind of work, you know, on an illustration in the same way, but your kVp doesn't drop on a falling load generator. What happens on a falling load generator is that they are designed, and I think they were originally implemented in departments that needed rapid exposures, very rapid exposures. I know we're almost out of time, I think. But what we get in a falling load generator is with the exposure, the machine is set to give you the highest possible MA at the outset of the exposure. So let's say you set you're making a big exposure. It doesn't even have to be a big exposure. Let's say you're doing, I don't know, cardiac catheterization, and you need to make an exposure. So what it's going to give you is the highest possible MA that the machine can give you. So the highest setting, your phototiming is going to give you the highest setting in MA that the machine allows. So the start of your exposure starts at 1000 MA, and throughout the exposure, the MA station drops, okay? Capacitor discharge, kVp drops. Falling load generator, the MA drops throughout the exposure. The purpose for this is because to limit motion, to give you the shortest exposure time possible. So if you shoot with 1000 MA and you shoot chest X-ray, your exposure time is going to be really, really quick. So if you're doing cardiac catheterization where the heart's moving at all times, you want short exposure, right? So that's the purpose for these type of machines. The problem with these is that you know, you're trying to learn technique now and next semester and throughout your 2 years in the program. If you're working with a falling load generator, you never know what your mass value is. When you make your exposure, it tells you what your time is, but it never tells you what your mass value is. So they're great for limiting motion, but for learning off of, not quite so much. Okay. Voltage ripple we talked about, so I won't go back through that. The chart on page 99, figure 5-29, kind of runs through all that. And really the only other thing is power rating. You know how to calculate power. Power is voltage times amperage, right? So current times potential. And how they calculate the rating for a generator is high voltage generators is, and that penguin there, is a maximum tube current at 100 kVp and 100 milliseconds. So any generator that you work with is always going to have power rating. That's how they calculate it. All right, any questions? There is a diagram on the test of the entire circuit. I did not take it directly out of the textbook, but if you know that figure on page 101 and you know where all those components are on page 101, then you're not going to have a problem really with the diagram on the test. Real quickly though, you know, the one thing in all that we didn't talk about was an MA meter. So all of the controls in the circuit work off a low voltage, okay? But notice where the MA meter is. Where is it? It's in the high voltage side, right? But because of the changing magnetic field with the alternating current on the secondary side, your voltage in the secondary side of the high voltage generator is always at 0, all right? Don't ask me how, I don't know. I don't really care. You just need to memorize it. It's always at 0 if it's wired dead square into the secondary side of the high voltage generator. It just is, okay? So is it in the low voltage circuit? There's questions on the test, very specific. Is it in the low voltage circuit? No, it's in the high voltage circuit. Does it work off of low voltage though? Yes, okay? What's the general rule for true false questions? The whole thing has to be or the whole thing is right. Okay, you've been warned. Okay, all right, any other questions? I think we talked about all the other components, didn't we?
Can you repeat that one more time?
Which part?
About
The, where it's wired in and why?
yeah.
Yeah, it's wired into well, it's wired into the high voltage circuit because we actually have to count the number of electrons that truly travel across the tube. We set our amperage in the low voltage circuit, you know, in the filament circuit. But what we need to know is how many actually made the jump across the tube. So we have to have it in the high voltage circuit so we count them as they return into the system. That's why it's wired into the high voltage system. But if it's wired directly into the middle of that high voltage, the secondary side of the high voltage generator, then the voltage is at 0, even though it's on the high voltage side, it works off the low voltage. So it's not in the low voltage circuit, but it does work off of low voltage. So again, I hate to give it away this blatantly, but I think it's true false question. It says all of the components that on the control panel work off low voltage. True?
Yes.
Yes. And are found in the low voltage circuit. False. Right. Okay. I think it's the way.
And that has to deal with amperage.
That has, yeah, the MA meters measuring the actual amperage. Yeah. Yeah. But it's in the high voltage section working off low voltage. Yeah. Because you gotta have both.
Yeah.
Yeah. All right. y'all Friday. Yeah. The creation doesn't occur until you make it. You adjust your voltage in anticipation of becoming a kilovolt, but you don't truly kilovolt.
Like, are all these like, I was a little bit confused on these. I don't know, like, with AEC and all these calls, because like, it kind of went off of, like, kind of,
Yeah.
I didn't know if I had to see it in consideration of like all these changes.
Right, right. So really, when you're utilizing the AEC, the only thing that you're gonna do that could affect your exposure to the image reception is two things. Manipulation of the density controls, plus one minus one, or manipulation of the cells. So you should check the tray and you use the center cell. Then, because you're penetrating through heart and lungs, or heart and spine, the exposure to the image receptor is going to be higher than if you were just using outer cells.
Okay, okay. Thank you.
Next year, I need to make a heading.
Yeah, I was a little confused
Yeah.
on it, but I kind of did like both, just to do.
Yeah.
Okay, it's with it, yeah. Yeah.
I guess it's good to know what's going on, like, I'm gonna study, no.
So is KDP and math, is that recognized separately or together?
Well, separately. Or, well, what are you, I'm not sure I understand the question.
Well, because this says, does it recognize the KDP and math separately?
Oh, the AECs, no. No, it doesn't. It's just, you know, I guess by the strictest definition, it really recognizes the mass because it's counting the photons basically. But it can't tell if you use a high KDP or low KDP. And that's kind of the spirit of the answer, or the question is does it differentiate high KDP and low KDP? The answer is no.